calculate. Let's calculate the deflection now. Okay. Let's go. So this is the meaning of what the gap is doing to us. Okay. What the gap is 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 complicating things. Okay. But it's not difficult to analyze. Okay. So the first thing we do, right? The first thing we do is step one. Uh, uh, okay. Allow free expansion or allow free motion. Allow free movement for uh, aluminum for members made of aluminum and stainless steel. Okay, we allow them to move. Okay, so now we're going to calculate. Okay, determine deflection due to temperature of aluminum and deflection of temperature due to stainless steel on stainless steel. Okay, so what we do is we are going to consider the aluminum. So what we are saying is for now, okay, there is no restriction. So this thing can grow whatever it wants. Okay, so we know that the temperature increase. We're going to determine the delta T of the aluminum. Okay. So this delta T due to aluminum or for aluminum is equal to the alpha. So the formula is alpha aluminum delta T multiplied by length of aluminum. Okay, length of aluminum. So the alpha is 23 times 10 to power minus 6. This is wrong, okay? This is not 16, okay? It's 10. Okay. And then the delta T, so the new temperature is what? The new temperature is 140. The original is 20. Okay. Then the length of the aluminum, we know that the length is equal to 0.3 meters. Okay. So this will be equal to 23 power of 23 power minus 6 times by 120 times by point. So it's equal to 828. Wait, 140 minus 20 times 0.3 times by 23 power minus 6.
Sorry, Eugene, Dr. Eugene. I know you converted to meters. You've been converting to meters, but for example, for this equation, if it's in Celsius, we have to keep it in meters. When do we know if it's gonna stay in millimeters than meters?
The
Because
length is in the length. Everything have to be calculated in meters.
meters, I understand. So, but let's just say I put it in Fahrenheit. I converted it to Fahrenheit or whatever. Can I still use it in meters?
Uh,
My alpha, my
if usually in Fahrenheit is in inches.
okay. That's
Okay,
what I wanted to know.
usually
Okay, thank you.
Fahrenheit is inches. Okay. So it's either you do imperial or you do matrix. They don't mix around. Okay. So now the delta T. Okay, we have found the delta T of the aluminum. Okay. And then next we are going to why is it? Oh, okay. Then we are going to do stainless steel. Okay. So we know stainless steel is on the other side. So again, we allow free motion. So the stainless steel is the aluminum is not actually there at all. Okay. So this is our stainless steel. Right. So it will move this direction. Delta T. Stainless steel. Now, whether it moves left or right is nothing to do with static analysis. There's nothing positive or negative. Okay. The change in temperature will induce a tensile, or the delta T will be positive, so it will increase in length. Okay, so don't have the impression if it's going towards the right it's positive. No. Okay, when there's an increase in length means it's tensile. When a decrease in length is compression. Okay, so delta T due to stainless steel is equal to alpha stainless steel multiplied by the change in temperature and N of stainless steel. So this will be equal to, so for stainless steel, we know it's 17.3 times 10 to the power minus 6, change in length, change in temperature, multiplied by the length. So we are given that the length down here is 0.25. So 17.3 power minus 6 times by 120 times by 1.25 is equal to 519. Okay, so it's equal to positive 0.519 times 10 to the power minus 3 meters. Okay, the top one is also positive. Okay. So from here, right? So we calculated the stresses that's allowed for free expansion. Okay. So we note the total, okay, the summation of the total deflection due to temperature is equal to we calculated what? Let me go back here. We calculated 0.828 times 10 to the power minus 3 plus by 0.519 times 10 to the power minus 3. So it's equal to 0.828 power minus 3 plus by 0.519 power minus 3. So this is equal to 1.347. Okay, 1.347. 347 times 10 to the power minus 3 meters. Okay. So the next thing that we have to compensate. Next, we have to compensate for the gap. Okay, we have to compensate for the gap. So we have to calculate. We have to include the. We have to include, or we have to compensate for the gap. Okay. So now, watch this. Okay. So if there is zero gap, okay, let me elaborate. If there is zero gap, okay, stresses will be induced in the structure up to a deflection, or up to a delta T of 1.347 times 10 to the power minus 3 meter. Right? So now, if there's a gap, of 0.5 meters or millimeters or times 10 to the power 3 meter, okay, from 0 to 0.5 or from or at, okay, if there's a gap of 0.5 times 10 to the power 3 meter, okay, down to 0, right, no stresses will be what? Okay, no stresses will be generated. Okay, so this is a important component to include. Okay, because it will change your delta T. Okay, no stresses will be generated. However, when there is no gap, okay, the stresses will be induced. Stresses will be generated. So therefore, right, delta T will be equal to what? 1.347 times by minus 3 minus by 0.5 times 10 to the power minus 3. So this is equal to 1.347 power minus 3 minus 0.5 power minus 3 is equal to 0.847 times 10 to the power minus 3 meters. Right? So what is this? Okay. So remember we drew this. Okay. Remember we drew this. So we drew this earlier. Okay. So I'm going to draw okay. So this is 1 minus 1.0 minus 0.8 0.6 0.4 0.2 0. Then you have 0.2 0.4 0.6. This is your gap. When a zero gap means there's stresses, right? So once we reach to here, okay, so this can be stress of your aluminum or stress of stainless steel, right? So when it is on this side, okay, when exactly on down here, you have no stress. When there's a gap, when your stress goes, when your gap goes negative, then there is what? Stresses, right? And if it's allowed free deflection, okay, if the things allowed go free, the heat will induce 1.347 times 10 to the power minus 3 of what? Of expansion for the aluminum and the stainless steel. Now, okay, now we are at what? We are at 0.5. Okay, where there's a gap at 0.5. And we'll finish off. So 0.5 is now the new reference point, not the new reference point. It's where we have a gap. Okay. And the final expansion will be at 0.847. Okay, so I'm going to sketch out the location of 0.847. 0.8, 0.9, 0.847 is here. Right? So this is at minus 0.847. Right? This is at 0.5. So the material both materials, okay, will contract, okay, or based on the gap. This is relative to the gap, okay. So as I mentioned before, down here there is no what? Over here there is no stress at all, okay. So once there's no more gap, okay, once the gaps goes to 0, right, then your stresses will start to bulge out. Okay, so one is for your, I don't know which one is for which one, okay, but this is one is for the aluminum,